At first, thank you very much for the kind invitation. Hi, everyone. Good afternoon. I'd like to congratulate the organizers for this nice conference. For me, it has been a nice afternoon. So I'll be presenting in broad overview of what we do at Center on Applied Photonics. So I begin to share the presentation. By the way, I'd like also to congratulate the others for still being with us. It's really a nice audience because at least here in Portugal, we have a beautiful day. Okay, so our INESC TEC motto is from knowledge generation to science-based innovation. This presentation is to frame our activity, because we are not a blue sky research institute, unhappily for us, physicists, but we have this idea that knowledge and technology and science can be something with economical, social relevance. So we have this nice name, Pervasive Intelligence with Social Relevance. Marketing guys work very good at INESC. So this is our interest, our mission. We don't want to have a Nobel Prize, okay, if it appears good, but we want really to do good science, develop good technology that can have some kind of social and societal impact. So this is our magic wheel, let's say. So from one side you have what we call the internally research clusters. They are the thrust, the motors of our research activity. And we have also some light structure, I could say our sales department, that are called Tech 4 platforms. So concerning the clusters, we'll be speaking about this one, Networked Intelligence System, because our center is in this. So these are the areas where the sectors of application of the economics that we develop things, and we have people that look at market and that go after opportunities to use our technology and our things. So this is the multidisciplinary environment that we have. As you can see, you have Network Intelligence Systems cluster. The first thing is Applied Photonics, and here we are. Only to give a brief overview, we have these numbers. We have also INESC P and D Brazil, and we develop work also with them. We have more than 350 integrated PhD, and with many more other researchers. And this interesting number, 200, is in average the number of people that get out of the system, let's say, and go to the universities to teach or go to companies to develop innovation. These are our main associates. We are, and these are our main customers, let's say, and these are our international connections. Our associates, we are a public interest society. So we don't have profit. We are not for profit, but really we are a private institution. So this means that we have as partners public universities, but really we are a private institution. So what we do, this is, I think, more interesting for you. So I'll be showing, and believe me, you'll find more interest in the presentations that our students will present. As you can see, this is our chain value or value chain, marketing and managerial, and all these kind of people like very much this kind of stuff. So we do some basic research, mainly applied research and some development. Our centers of INESC are more oriented to technology transfer and valorization. Our areas of activity are optical fiber sensing.
Professor Igneo, I'm sorry to interrupt. We lost your share screen. I don't know if you were still sharing.
I tried to share another screen.
Okay.
Let me see. Let me try again. And now, can you see?
Okay. Now we can.
Okay, I'll try the presentation mode. Okay, you can see now? Is it okay?
Yeah, perfect.
Okay, so this is the kind of stuff that we like to present to our partners and our industrial and economical partners. But mainly what it says is that what I want to stress is that we are focused on applied research and development, not so much on the, as they call technology research levels higher than 4 or 5. We work on optical fiber sensors, integrated optics, microfabrication, imaging, and quantum technologies. With these foreseen applications. I said that we are not a blue sky research institute, meaning that we don't strive only for knowledge. We strive for knowledge that can be applied. But this does not mean that we don't do basic research. If it's needed, we'll do after that. Concerning areas, we have this area of quantum things, let's say, and also nonlinear photonics. Ariel is our research leader. Here we are more related to simulation. We have also some experimental work concerning these areas, but these are our most theoretical guys, like we like to call them. Not necessarily in a good way, but okay, they like it. What we have more, what we can, now my computer decided not to, okay. So also this group is dealing with quantum plasmonic concerning optical metamaterials. And in this case, we have some experimental work based upon the simulations and models that we develop. After that, we, for more than 20 years now, we have been working on optical Bragg ratings, mainly in fibers. This was our main theme of activity during several years. Now we are focusing on other things. But by the way, this led to the foundation of a company, Fiber Sensing, that now belongs to HBM Group. And it's a startup that was created by 2 of our PhD researchers, physicists from our department. So these were our dinosaur technologies that we're using, but we still use. They are still very interesting. We have also, okay, my computer doesn't like to help. I like this picture because it's a kind of one in all, or all in one, things that we can do. We can design and can manufacture, fabricate within our facilities of these kind of things. A component that is based on fiber, that you can apply a thin film, that you can functionalize the surface with nanoparticles, that you can polish, so on and so on. We have here an example of thrombin. Thrombin is the thing that is related to blood clots. So it's an interesting application. We have also worked in physical sensors, fiber endoscope sensing, microfabrication. Paul Marques is the professor that works in this. We have a nice microfabrication machining infrastructure. Here are some of the nice pictures that you can see that we developed. They can be used for many things. More nice pictures. We also use not only femtosecond writing, but also multiphoton photopolarization. One of the latest applications was optical fiber tweezers. By the way, this led also to the creation of a startup from a PhD student from here called Dilov. We have many work in the imaging concerning mainly OCT and other interferometric imaging that we have applied for many industrial applications. And lately we have been working on LIDs. This is very interesting for many, many areas of application. And we are having projects with people from geology, from the cork industry, from the agriculture, and so on. So please, I'll put my email, but be free to speak and to tell us. But you will find more interesting things from three guys that are going to speak. Thank you very much.
Thank you so much, Professor Irineu. So if you have any questions, just write to his email. Now, Tiago Freire, are you there? You want to share your screen?
Yes, I'm here.
Okay.
It is in full screen, I guess.
Yeah, perfect. Go ahead.
So, hello, my name is Tiago. My name is Tiago Freire. I am a PhD student, and I will present the work that I and the group where I work does at INESC TEC. Before that, I would like to thank the PLANCKS organizers for this event and for the opportunity to be here presenting my work. So at INESC TEC, I work in the Center of Applied Photonics in the research group of quantum engineering and technology. And our aim topics of research are materials for sensing, the nanophotonics for our quantum sensing, and our quantum computing, the development of high-performance solvers, and studying of quantum artificial intelligence. And my work is inserted in this tool where I use high-performance numerical solvers to study fluids of light as a platform for developing optical analogs, and the goal is to use these systems for emulating other phenomena, such as superfluid effects or some gravitation phenomena, such as black holes. So, how light can behave as a fluid? Well, by itself, this is not possible because a fluid requires particles with mass and interaction between them. So, how do we overcome this issue? Well, let's consider a beam of light propagating inside a nonlinear material, here represented in this figure. Under the paraxial approximation, the dynamics occurs in the transverse plane. So the diffraction in this plane gives rise to an effective mass. And the nonlinearity of the medium will variate the required interactions between the photons. So in these conditions, the transverse component of a light beam can be interpreted as a fluid, and the propagation direction in this figure represented by Z will play the role of time. This means that each slice along the material represents a fluid at different moments in time. So if we consider a light beam described by this form, the fluid density will correspond to the beam intensity, and the fluid velocity to the gradient of the phase of the beam, where this fluid velocity can be controlled by adjusting the angle at which the beam enters the material. So how do we model these systems? Well, under the paraxial approximation, the beam envelope can be described by a nonlinear Schrödinger equation, where this constant beta related with the diffraction in the transverse plane is proportional to the effective mass of the photons, and these local and non-local linearities mediate the interaction between the photons. So the goal is to find suitable optical materials that are described by a similar model for creating fluids of light. And in my work and in collaboration with the rest of the group, we have been exploring the possibility of using nematic liquid crystals. These materials are non-local, where the effect extends beyond the beam waste. They are described by a nonlinear Schrodinger equation, and they are interesting in this context, since by applying an external electric field, we can control the nonlinear response of the system, which is very useful for analog computing. So in an initial work, we started by exploring the possibility of nematic liquid crystals to support fluids of light. We calculated the expression relation of we calculated the expression relation and proposed a new method of measuring in an experiment, and showed that nematic liquid crystals can indeed support fluids of light. Furthermore, by using the Landau criteria, we also showed that these fluids of light can support superfluid phenomena, since they have a critical velocity below which the fluid behaves as a superfluid. So in the subsequent work, we explored the consequences of having an optical effect in the medium in the one-dimensional setup, and showed that for velocities below the critical velocity, this force goes to zero. This indicates that we are in the superfluid regime. In a different setup, now in the two-dimensional system, we also observe that the light fluid in the predicted superfluid regime passes through the defects without noticing, as expected from a superfluid. And as we increase the velocity, we see the breakdown of a superfluid regime to the emission of vortices with quantized circulation. This is a hallmark of superfluidity, and these results suggest that nematic liquid crystals can be used to emulate superfluid phenomena. Currently, we have been exploring the possibility of using these light fluids to study the larval regimes, and proposed a new experimental method to excite these regimes. This method consists in propagating two fluids of light with different velocities that will interact with each other, and from this interaction results instabilities that will lead to the carbon regime. And we were able to observe the energy cascades that are characteristic of the carbon regimes. And we are also considering this as a setup with non-local linearities supported by nematic liquid crystals. Here we have the expression relation of the two fluid systems, and by controlling the fluid velocity, we can have different inputs of energy in the system that will generate different types of carbon regimes. In the different topic, we also explored the possibility of using a train of solitons in local optical materials for reservoir computing. Simply, the idea is to encode a certain state in the position of the solitons at the entrance of the medium. This state propagates in the medium, and we measure the output at the exit. Then this output is transformed into a forecast via the transformation matrix that is obtained by a training procedure. And in this work, we were able to apply this for performing a classification task of a two-class spiral data set. On the other scope, we have a collaboration with Centro de Física the Universidade do Minho do Porto through Professor Orfeu, and we have been using the numerical solvers developed for for the previous studies for exploring non-minimal curvature matter gravity models. These models could assist in generalizing the action from the general relativity to into more complex versions or fit that are characterized by these functions of the Ricci scalar. However, the resulting field equations are very complex and are to study by the usual means. But under specific conditions, the field equations can be approximated by hydrodynamic descriptions, and this is useful since by applying the model transformation we can convert these equations into a generalized Hardinger equation, and the previous solvers can be used. And we have applied these solvers to study the dynamics imposed by these gravity models and compare the results with expected results from general relativity. And more recently, we have used these solvers to search for the existence of static solutions that these gravity models may support. So thank you for your attention. And if you have any question, feel free to ask me or contact me through my email.
Thank you, Tiago. Thank you so much. Is there any questions? We still have 5 minutes.
I will put my email in the chat.
Thank you. Thank you. Okay, Ali said, well, very interesting. Okay, if you don't have any questions, I'll give the word to Paulo. Paulo, are you there?
Yes,
Perfect.
I'm here.
Thank you so much, Tiago.
Thank you.
And Paulo, you can share your screen. Perfect. Everything is okay? Go ahead.
Good evening. I'm Paulo Rebolinho, and I will talk about the Vernier effect and how we can use these effects to obtain giant sensitivities. So I will start to describe the Vernier scale and Vernier effects. After, I will talk about the first steps in optics and how the Vernier effect implementation in interferometry. After, I will give some examples about traditional and enhanced Vernier effects and finalize with a conclusion. So, the Vernier scale was invented by Pierre Vernier in 1631. And it is consists of a combination of two different scales. Like we can see in this animation, the reading starts by relate the first line, red line with the blue line, and then to improve the measurement resolution, we seeing which the red line is in phase with the blue line. Of course, this is the discrete measurements, but in optics, we use the continuous measurements, and this is named the Vernier effect. This is composed by two cavities. The orange line represents the reference cavities, and the blue line represents the sensing cavity. The overlapping of these two spectral signals resulting in the Vernier effect that are represented by the green line. The first steps in optics was in lasers. The utilization of two cavities allow better control in the transverse mode amplifications. At the same time, appears some sensor that exhibit this Vernier effect, but only in 2011 appeared the first paper that described the implementation of Vernier effects in optical fiber sensors. So Ziyuan Zhang and his colleagues developed a sensor that achieve a sensibility close to 6,000 nanometer per refract index, which is much higher when compared if they use only a single sensor. After some years, André Gomes, our colleague, published a paper that described how can we implement the Vernier effect harmonics to improve the sensitivity. Like we can see on the right side, the fundamental wave that the most common and most used in the Vernier effect. Above we have the first, second, and the third harmonic. Like we can see, higher orders imply an increase of wavelength numbers, and the fundamental wave appear when the sensing cavity of a length close to the reference cavity length. The first harmonic appear when the sensing cavity length is close to double the length of the reference cavity and has 2 times more sensibility than the fundamental. The second harmonic appear when the sensing cavity length is close to the triple of the reference cavity length and has 4 times more sensibility than the fundamental. And finally, the third harmonic appear when the sensing cavity length is close to the quadruple of the reference cavity length and has 8 times more sensibility than the fundamental. After some months, in 2020, appear a new paper that divide the Vernier effects in 3 cases: reduce, traditional, and enhanced Vernier effects. The traditional Vernier effect is the most common published at that time, and like I say before, is composed by the reference cavity and the sensing cavity. On the left, we have the reduced Vernier effect that is composed by 2 cavities that move in the same direction and result in the envelope that is stationary. On the right side, we have the enhanced Vernier effect that is composed by 2 cavities, which this fringe moves in the opposite directions. And the result is this envelope sensibility much higher than the traditional Vernier effects. So, an example of the traditional Vernier effect is our drop structure optical fiber sense, and this is composed by a drop microstructure that is coupled to, that is fused to the end of the optical fiber end. And inside of this structure is the reference cavity. The sensing cavity is between the end of the optical fiber and the mirror or a given reflective surface. With this sensor, we can generate, the fundamental, the first harmonic and second harmonic, and highlight the sensibility of second harmonic that is 28.3 nanometer per micrometer, which is 2 times more sensible than the other higher sensibility optical fiber sense. After this, we start to explore the enhanced Vernier effects In this case, we start to implement the enhanced Vernier effect in the strain optical fiber sense. Typically, the strain is applied in the sensor ends, but in this case, we apply on the middle. And with this, we develop the combination between the push-pull method and the Vernier effect. Is this when the middle go to the left, in the red fiber, the strain decrease, and the blue fiber, the strain increase. So taking account this fiber is equal, is the same fiber, is this we use two equal bow tie fibers. So we have the cavity that move in symmetrical, that have asymmetrical movements. So we have a maximization of the enhanced Vernier effects. With this sensor, we obtain a maximum sensitivity of 10,000 picometer per microstrain, which is much higher when compared with other strain optical fiber sensing that use the Vernier effect, that only achieve a maximum sensitivity of 117 picometer per microstrain. After this, we implement this concept in displacement optical fiber sense. We use two Fabry-Perot interferometer, and in the middle we have the reflective surface. With this setup, we obtain the maximum sensitivity of 254 nanometer per microstrain, which is much higher when compared with the other sensor that use the traditional Vernier effects. So in the final, I highlight three main characteristics of Vernier effects. This effect needs two sensors in parallel or in cascade. The envelope sensitivity is higher than the sensitivity of a single sensor, and higher sensitivities are obtained with higher orders, harmonics, and the enhanced Vernier effects. Thanks for your attention.
Thank you so much, Paulo. Does anyone have any questions? You should be able to unmute and turn on your video if you do. No questions? Well, thank you so much, Paulo. If you want, you can write your email on the chat, like everyone else, to receive any questions. And now I give the word to João Maia. João Maia.
Thank you, Sophia. So, hi everyone, my name is João Maia. I am a PhD student here at INESC TEC. For the past 5 years or so, I have been working in the microfabrication group. And today I will give an overview about the work we have been conducting and more focused on the applications in autofluidics. So I think the best way to start this presentation is to explain what I mean by autofluidics. And here we have two examples of autofluidic devices, which I took from two well-known articles. Here you have a monolithic optical stretcher made in a fused silica planar substrate. The device consists of a microfluidic channel where you inject red blood cells dispersed in an aqueous medium, and you use light traveling through an optical waveguide to trap these cells and to study its properties. And through this study, you can relate the gathered optical properties to the health state of the cell. On another application made also in a fused silica substrate, you have a Mach-Zehnder interferometer where you have light traveling from an optical fiber into an wide junction, which splits the guided beam into two arms. One of those crosses a microfluidic channel, whereas other goes above the channel, and at the output both signals recombine, and you can and by changing the refractive index within the microfluidic channel, you can change the interference condition, and that way we can measure through the output spectrum any variation in the refractive index of the fluid that can be caused by alteration in the concentration of, for instance, an agent mixed within the fluid, or alteration in temperature, or whatever. So basically what I mean by autofluidics, and what the goal of this presentation is to showcase how you can use ultrafast laser inscription to form in either a single planar substrate or in an optical fiber devices that combine integrated optical systems with microfluidic systems. So these devices can be formed either through photolithography or etching. In the case of microfluidic channels, we also can fabricate them through soft lithography or other micromolding techniques. But here I will focus on the work we've been developing in ultrafast laser inscription. So this image here shows basically this fabrication technique. Obviously, the fabrication setup isn't as simple as this one, but it shows in essence what I mean by laser inscription. We have ultra short pulsed beam, or a train of ultra short pulsed beams that is focused inside a transparent media. And to fabricate these autofluidic devices, what we are relying on is on the interaction between the laser and the irradiated medium to change the properties of the material, and that way you can fabricate different types of devices. So this is a technique that has to be applied to transparent media, and this is actually a very important feature of the technique. So and not only that, there is a reason also why we need an ultra short pulse beam. So for instance, I will speak about the results we have obtained in fused silica. Fused silica is a transparent medium in visible and in the near infrared. So you cannot, so the medium cannot absorb light from the 550 nanometer beam we use. So in that sense, linear absorption is not allowed. Not that we are interested in either way, because if we had linear absorption, then basically the entire medium that was irradiated by the laser beam would be modified. And so that way we would not be able to fabricate structures with micrometric precision. Here, what we are interested in is in processes driven by nonlinear absorption. So, and that's why it's important to have transparent medium. However, to have these types of processes, you need high peak intensity. That's why you need to use an ultra short pulse beam. Here we use a beam with a pulse duration of 220 femtoseconds. And that is also why the beam has to be tightly focused within the sample. The importance of nonlinear absorption, as I said, is that it will confine the laser-induced modification only to the focal volume. And so this way we can fabricate structures with micrometric precision. Not only that, and this is also where it sets apart from other techniques such as photolithography and etching, this allows us to, nonlinear absorption allows us to modify the properties within the volume. So it's not just a surface processing technique, but also volume processing one. And if we translate the material in relation to the laser focus, we can form pure three-dimensional devices along a user-defined architecture. So it's a technique that can be applied to either glasses, crystals, or polymers, either in planar substrates or in optical fibers. But here I will only focus on the work we have been developing in planar fused silica substrates. So as I said, the devices we can fabricate rely on the nature of the laser matter interaction. And in fused silica, one of the possible modifications you can have is related to an increase in the refractive index. Here, for instance, we have a cross-section picture of the laser modified volume, and you see this bright region here is associated to an increase in the refractive index of around 0.01 or 0.015. So this increase allows us to form already integrated optics devices, because as you can see, just because we have a localized index increase, you can have light being confined to this region here due to total internal reflection. So we have exploited this modification to fabricate optical waveguides, where light is guided through the irradiated path, as shown here. So here light is only guided through this line. Here you have an example of a straight waveguide, but we can also form banded waveguides. If we now modulate the laser train pulse, we can also fabricate Bragg ratings, as shown here, where we can have a reflection at a very narrow wavelength range. We have applied this technique to fused silicon to borosilicate glasses, and in the case of optical waveguides, we can fabricate them from the visible to the infrared, to the near infrared, and with very low insertion losses. In the case of the Bragg rating waveguides, we have also fabricated them in fused silica, in optical fibers, and actually in optical fibers, we are also able to form long period gratings where light is coupled from the core to cladding modes of the fiber. So due to the three-dimensional scanning opportunity, you can also form power splitters such as wide junctions, directional couplers, or as shown here, multi-mode interference devices, where light traveling through this waveguide, when reaching this multi-mode region at the output, we will have three spatially separated beams with equal power. On the other hand, we can also fabricate more complex devices such as ad hoc filter, as shown here, which can be used for wavelength multiplexing and for signal routing. So this is one of the possible modifications, and in itself, it already allows us to form integrated optical devices. The other possible modification you can have in fused silica is related to the formation of nanogratings. So as you can see here, you have these periodic nano layers, which are darker in this picture, and there are self-organized layers of modified silica, in this case porous silica, and the existence of this structure is what allows us to fabricate microfluidic channels. As you see here, when we immerse the substrate in HF acid or in a potassium hydroxide at high temperatures, these layers will be etched at a faster rate than the pristine medium. So in essence, ultrafast laser inscription also allows us to generate etching selectivity where, as shown here, the laser exposure tracks are removed at a faster etch rate than the remaining material. So now if we follow a configuration where we closely stack multiple laser exposure tracks, in this case with a gap between 3 and 5 micrometers between them, and because this modification also shows long range order, we can form microfluidic channels with any size, and by changing the way we stack these tracks with any shape as well. Here, for instance, we have a cross-section picture of the microfluidic channel that was made in fused silica substrate. Here we form the channel at the surface of the substrate, but we can also form it within the substrate itself. If we now follow more complicated design schemes, we can also engineer microstructures within the channel. For instance, here, if I now leave a small silica core unirradiated, so as you see in this picture, there is a gap that we left unexposed. When we do etching, we will gonna end up with a silica core suspended core attached to both sidewalls of the microfluidic channel. One of the problems that we have, though, and this is actually a problem related to most glass machining processes, is that the surface roughness of this core is actually pretty high, and you actually saw that already in this top view image that shows the surface of the microfluidic channel. So because we have a high surface roughness, this can limit the application of these devices, as this can introduce optical scattering and really limit the application of the device for optical applications or for autofluidic applications. So what we then do to reduce this roughness is to perform thermal annealing at the temperature close to the glass point of fused silica, so it's around 1250 degrees, and we are able to reduce the surface roughness to around 10 nanometers, as you can see here, where we end up with a very smooth structure. So we can use then these microstructures for different applications. For instance, here we have a suspended waveguide that is written within the microfluidic channel, and we also have a femtosecond laser written one that can be used to couple light to the suspended waveguide. Because the silica core has a higher refractive index than the surrounding medium, we can have waveguiding through this suspended waveguide. And by changing the refractive index of the medium inside the microfluidic channel, we can also reconfigure the properties of the waveguide. So additionally, we can fabricate waveguides with a diameter as low as 2 micrometers, which is actually pretty close to what you have with interpret fibers fabricated through the heat and pull method. The other opportunity is to fabricate microstructures at the bottom of the channel that can be used to change the flow dynamics of fluid circulating within the channel. So, so far I have shown two possible modifications that separately allow us to fabricate either integrated optical devices or microfluidic channels. But as I mentioned in the beginning, what we are interested in is in fabricating autofluidic devices that merge these two types of structures. Over the past few years, you have fabricated various examples of optofluidic devices, but in this talk, I will only focus on our most recent work, which is related to monolithic whispering gallery mode resonator. Here we have a scheme of that device. We have a microdisc resonator, and we have coupled to the resonator a suspended waveguide, where light is coupled into from within waveguide and out of the waveguide for lead out. So for those of you who don't know, microdisc resonator also, within the microdisc, we can also have optical modes propagating within the disc, but differently from the waveguide, these modes travel around the surface of the disc due to total internal reflection as well. The difference being that it travels around the surface. To excite this type of modes, usually you rely on prism coupling techniques, or you rely on the evanescent field of a tapered waveguide. But usually in those schemes, you don't have a permanent alignment. It is a rather bulky coupling approach. What we propose here is to have a suspended waveguide permanently coupled, and this can be more useful if you now try to use these devices for real-life applications. Not only that, because it is made of fused silica, we can also guarantee that the device will be biocompatible, that it is inert to most solvents, and it also shows other properties related to strength and hardness. So to do this, though, there are a couple of requirements that we have to verify. To couple light from the waveguide to the microdisc, the gap between both structures in most cases is less than 1 micrometer in order to have the mode profile of both optical modes overlap, and to also maximize the mode profile of the mode traveling through the suspended waveguide. its diameter should be around 1 and 2 micrometers. So the fabrication of this device is similar to what we have presented, what we have discussed so far. We first perform femtosecond laser direct writing to machine the microfluidic channel. We then perform chemical etching to expose the microdisc in the suspended waveguide. We do thermal annealing to decrease the surface roughness. And at last, we write the lead in and the lead out waveguides to access the suspended waveguide. So, however, if we go for a configuration where the waveguide is initially designed tangent to the microdisc, as shown in this picture, where each of these tracks corresponds to the path of the laser beam, then because the HF acid can also etch through the pristine medium, after etching and after thermal annealing, we end up with a gap of around 2 to 3 micrometers in between both structures. And this gap is too large and prevents us from exciting whispering gallery modes. So in order to to realize this device, we need to also alter the way we design it. So after a lot of work, we have observed that the best way to write it is if we now fabricate the waveguide a bit embedded within the microdisc, but with an arc segment that follows the disc's curvature. So after chemical etching, you also have a gap between both structures, but as you can see here, after thermal annealing, viscous induced flow will cause the waveguide to realign itself, and if we do things carefully enough during etching, we can have the waveguide end up tangent to the microdisc as shown here. Not only that, in the design, if we change the width of the arc segment, we can also shape the waveguide within the coupling region, and this way we can maximize even further the coupling efficiency. So this type of devices can be used in multiple applications, for instance, in optical sensing or in biosensing, because it gives you a very high quality factor that is associated to a very high, very low, in this case, limit of detection. It can also be used for lasing applications if instead we have a disk made of an active medium, but so far we are yet to reach those applications. So far we have only showed its potential for optical sensing. Here you have an image of the transmission spectrum where you can see that we have very sharp resonance that are associated to a quality factor of around 100,000. And so this is what we are interested, particularly in optical sensing applications. We have a very high limit of detection. Here we have the results we have gathered so far related to optical sensing. This sensing arises from the fact that the whispering wavelength of the excited whispering gallery mode resonance depends on the index contrast between the disk and its surrounding. So this will dictate the effective refractive index of excited modes. And yeah, as you can see here, the resonance, we can monitor changes in the refractive index by monitoring the shift in the peak wavelength. And as you can see here in the curve in red, we have a high quality factor around 100,000 throughout a very wide refractive index range. So just to end, ultrafast laser inscription is a versatile technique, can be used to form three-dimensional devices with micrometric precision, can be applied to a wide range of materials. In this talk, I only focused on the fabrication in fused silica, but we have also fabricated devices in borosilicate glass. We have fabricated in silica-based fibers, and recently we have also been working with polymers, where femtosecond laser can be important to assist in the polymerization process. I also focus on applications regarding autofluidics, but as you could see, this technique can also be used to form integrated optic devices, microfluidic devices. Microfluidic devices, when combined with polymer microstructures, can also be important. And yeah, that's pretty much it. That's what I had to say. And feel free to ask any questions.
Thank you, João. Thank you for your very interesting talk. Is there any questions? Are there any questions? If so, you can unmute directly and ask questions. Okay, João, if you want, you can leave your email on the chat so that
Okay.
someone has a question.
Yeah, okay.
Okay, thank you so much.